In part 4 of Unit 3, we're going to go over limiting reactants. The limiting reactant is the reactant that's used up first in a reaction, causing the reaction to stop. It's the reactant that we run out of first. The other reactant that's left over once the limiting reactant is gone is called the excess reactant. We can do calculations to find the maximum amount of product that's going to be formed. That maximum amount is called the theoretical yield. There are two ways to solve a limiting reactant problem. The first way is to use a have-need table, which is what we're going to look at right here. In this question, 5 grams of hydrogen and nitrogen combined, we need to find the theoretical yield of ammonia. Again, first thing we have to do is make sure our equation is balanced. Now, in the have-need example, we're going to convert the 5 grams of hydrogen and the 5 grams of nitrogen into moles and see how many moles we're starting off with, how many moles we have. So 5 grams of hydrogen. We need to convert that to moles. 1 mole of hydrogen has a mass of 2 grams. So 5 divided by 2 is 2.5 moles of hydrogen. We need to do the same thing for nitrogen, which we have 5 grams of. Converting that to moles, 1 mole of N2 has a mass of 28 grams. So that's going to give us 0.18 moles of nitrogen. Now, these values right here, that's how much of each reactant we're starting with. That's what we have. What we'll do now is the mole ratio between the different reactants to figure out how much of the other we'd need to get rid of what we have. So for hydrogen, we're going to do the mole ratio between H2 and N2. We want to cancel out moles of H2 and figure out how many moles of N2 we need. So we're going to take this 3 from H2, put it here. The 1 from N2 goes here. So 2.5 divided by 3 is going to give us 0.83 moles of N2. We'll do the same thing down here. We want to cancel out moles of N2 and get to moles of H2. Take the 1 from N2, the 3 from H2. 0.18 times 3 is going to equal 0.54 moles of H2. I know the edge of the page kind of crept up on me there, but these two values that we just found, that's how many moles we need to get rid of what we have. So let's compare these two. To get rid of 0.18 moles of nitrogen, we need 0.54 moles of hydrogen. We have a whole lot more hydrogen than we need. Let's look at it the other way. To get rid of 2.5 moles of hydrogen, we need 0.83 moles of nitrogen. We don't have 0.83 moles, we've only got 0.18. The reactant that we don't have enough of is going to be our limiting reactant, because that's what's going to run out first. So we're going to run out of nitrogen and have hydrogen left over once the reaction is finished. Once we've identified the limiting reactant, we're going to take this value, the 0.18 moles of N2, and convert it to whatever we need. In this case, the theoretical yield of ammonia in H3. So let me clear this off and then we'll do that. So we're going to take our 0.18 moles of N2. We identified this as how much we have of the limiting reactant, and we're going to convert it to grams of NH3. So we're still dealing with a reactant right now. We have to do the mole ratio step. We want to cancel out moles of N2 and get to moles of NH3. Put our 1 from N2 there, the 2 from NH3 goes up here. Now we want to convert moles of NH3 to grams. 1 mole of NH3 has a molar mass of 17 grams. So 0.18 times 2 times 17, it's going to equal 6.12 grams of NH3. That is our theoretical yield. That's the maximum amount of product we can make based on the amount of the limiting reactant that we had. Now we're going to solve the same problem using what I like to think of as the long way. You have to do longer dimensional analysis problems in this method, but we know we've got 5 grams of each reactant. So what we'll do is 2 separate dimensional analysis problems and take each one to grams of NH3. So we'll start with hydrogen. In any stoichiometry problem, first step is usually convert to moles. So we want to get to moles of hydrogen. 1 mole of H2 has a mass of 2 grams. Our next step is the mole ratio to switch from hydrogen to NH3. So we want to get rid of moles of hydrogen and get into moles of NH3. We're going to take the 3 from hydrogen, put it here, the 2 from NH3, put it there. And then our last step is to go from moles of NH3 to grams, which is 17 grams per mole. So 5 times 2 times 17 divided by 6, or divided by 2 times 3, is going to give us 28.33 grams of NH3. Well, we don't really know where that number came from. We didn't see it on the last page, so let's go ahead and start with the other reactant. 5 grams of N2. We're going to do the same steps. We're going to take this all the way to grams of NH3. So first we got to convert to moles. 1 mole of N2 has a mass of 28 grams. We have to do the mole ratio. We want to cancel out moles of N2 and get to moles of NH3. Take the 2 from NH3 here, the invisible 1 from N2, put it there. And then our last conversion factor is going to be identical to this one, 17 grams per 1 mole of NH3. All of our units are going to cancel, and when we solve this, 5 times 2 times 17 divided by 28, we're going to get 6.12 grams of NH3. Hope that number looks familiar, because that's what we got when we use the have-need method. So when we use this long way, where we take the mass of each reactant all the way to the mass of the product, whichever reactant gives you the lowest amount of product, that means that that is your limiting reactant, and all this work up here means nothing, because we're not going to get 28.33 grams of NH3. We're going to run out of reactants once we get to 6.12 grams of NH3. So that means this is our theoretical yield, and N2 was the limiting reactant. To find the amount of the excess reactant that's left over in a reaction, what we need to do is subtract the moles of the excess reactant that was used from the moles of the excess reactant that we had to start with. So in our favorite reaction here, remember we'd found that we had initially 2.5 moles of hydrogen. We had just converted 5 grams into moles. And we know that hydrogen is our excess reactant when we've got 5 grams of each of these. So what we need to do is we need to figure out how much hydrogen was used up by the limiting reactant. Our limiting reactant was 0.18 moles of nitrogen. We're going to do the mole ratio between the two reactants this time to figure out how much hydrogen gets used when we get rid of 0.18 moles of N2. So we want to cancel out moles of N2, get to moles of H2, take the invisible 1, put it there, and the 3 from H2, put it there. So 0.18 times 3, that's going to equal 0.54 moles of H2. That's how much hydrogen was used in the reaction to get rid of our limiting reactant. So to find the excess reactant left over, we're going to take the moles of hydrogen that we started with, subtract the moles of hydrogen that got used up, and we're going to be left with 1.96 moles of hydrogen left over. Some questions may ask you to find the mass of the excess reactant left over. You'd still do this the same way, except at this step you would then convert 1.96 moles of hydrogen to grams. 1.96 moles. We'd cancel out moles of hydrogen using the molar mass. 1.96 times 2. It's going to be 3.98 grams or something like that. Another important calculation we need to do in stoichiometry is finding the percent yield. To find the percent yield, you divide the actual yield, which is how much of a product you actually recover in a lab setting, divided by the theoretical yield, which is what you calculate using stoichiometry. It's the maximum amount of product that can be formed. You can multiply that by 100. So the actual yield is how much you actually recover in a lab setting. Theoretical yield is the most you could possibly get. So thinking back to the reaction we'd been working with, let's say that we recovered 4.5 grams of NH3. That 4.5 grams is going to be our actual yield. That's how much we recovered. Our theoretical yield was 6.12 grams. That was the most we could get. If we multiply that by 100, we'll find our percent yield, which in this case turns out to be 73.5%. Your question for this section: which reactant is limiting in the following reaction? I've balanced the reaction for you and gave you the initial masses of both reactants. Just identify what the limiting reactant is.